Good evening, students. Our today's topic is charge and field. This charge and field chapter is the foundation for the remaining chapters in electricity. This chapter contributes 1 to 2 questions. In NEET exam. It contributes its weightage 1 to 2 questions in NEET exam. But this is foundation for the remaining chapters in electricity. And in this charge and field chapter, generally, the questions in NEET are formula-based, concept-oriented, and in this, we need to use vector analysis also. Vector addition and vector resolution we need to use in this chapter. And the most important thing regarding this chapter is, this chapter need to orientation, if you take, NCERT revision is important. Because in this chapter, questions are given earlier based on NCERT lines. Questions on NCERT lines, questions on based on the diagrams in NCERT book, graphical questions, these are important. And in this chapter, you need to focus mainly on Coulomb's law. Then field, intensity of electric field. Coulomb's law, intensity of electric field. And then on dipole, electric dipole. And then on Gauss law. This dipole mainly torque acting on dipole in uniform field. You should concentrate more on that. And in this field, intensity of field due to point charge, intensity of field due to linear charge distribution, that is a charged wire, intensity of the field due to charged plane sheet, intensity of the field due to spherical charge distribution. These areas you have to focus in this field, electric field. And some basic conceptual questions like properties of charge means charge possessed by any substance in nature must be integral multiples of electron charge. Charge is quantized. That charge, if Q is the charge possessed by any substance, it should be some integer into 1.6 into 10 power minus 19 coulomb, where n is an integer which represents the number of electrons either given to a substance or removed from the substance. These fundamentals you have to revise. Charge is conserved. There are different methods to charge any substance, no? Charge by frictional electricity, that is rubbing one substance with another suitable substance having different electron affinity. Then the two substances get electrically charged. Suppose if glass rod rubbed with silk, glass is positively charged, silk is negatively charged. Silk gains electrons from glass because silk has more electron affinity than glass. Both become charged, both gain, the two substances which are rubbed gain equal amounts of opposite nature charges. And this is charging by rubbing, and charging a substance by conduction, charging a substance by induction. These areas you revise. And whenever you charge any substance by any method, the total charge of system is conserved. Charge is conserved. So revise these important points. And when it comes to electric field, electric field lines, their properties, revise them. Electric field lines, their properties. Electric field lines start from positively charged particle. They end at negatively charged particle. Say this is one positively charged particle, this is negatively charged particle. Field lines start from positive charge and end at negative charge. They diverge from positive charge and converge towards negative charge. And most important, electric field lines are not closed curves, they are open curves. Electric field lines are not closed curves. Magnetic field lines are closed curves, but electric field lines are not closed curves. Why they are not closed curves? Suppose if the electric field line is a closed curve, the field line must start from one charge and end at that charge only. That is impossible, no? That is one reason. Second is electric field. Electric field is conservative field. Electric field is conservative field. And in conservative field, work done by conservative field to move a charge on closed path is zero. Work done by conservative field to move a charge on closed path is zero. Suppose electric field lines are closed curves if you assume, they are closed curves if you assume, then the work done to move a charge on that closed path is not zero. Work done to move a charge on closed path is not zero. That indicates the electric field is not conservative field, because work done by conservative field to move a charge on closed path is zero. So electric field lines are not closed because electric field is conservative field. That is the reason. So these areas you revise: properties of charge, properties of field lines, revise them. And another is intensity of electric field in different cases, relations. Intensity of electric field in different cases, relation with distance. Suppose in the field of point charge, in the field of one point charge, intensity of electric field at a distance is 1 by 4 pi epsilon naught Q by R square. This is the force experienced by unit positive charge due to this point charge Q. Force on unit positive charge, intensity of electric field E. So in the field of point charge, intensity is inversely proportional to R square. Whereas in the field of dipole, electric dipole, suppose two equivalent Opposite charges separated by some distance. This is dipole, no? On the axial line of dipole, intensity on axial line of dipole, formula you know now, 1 by 4 pi epsilon naught 2p by r cube, where p is electric dipole moment. Intensity at any point on this equatorial line of electric dipole. Intensity at any point on equatorial line of dipole. 1 by 4 pi epsilon naught p by r cube. Intensity in the field of dipole is inversely proportional to cube of the distance. In the field of point charge, inversely proportional to square of distance. In the field of dipole, inversely proportional to cube of distance. And in the field of line charge, means suppose you have a long charged wire. In the field of this long charged wire, intensity at a point which is at a distance r is lambda by 2 pi epsilon naught, or lambda is the charge per unit length, linear charge density. So in the field of line charge, intensity is inversely proportional to r. And in the field of plane charged sheet, if you have a plane charged sheet, in this field, intensity is independent of r. Intensity proportional to r power 0, I'm writing. Intensity is independent of the distance of the given point in this field. And similarly, in the field of hollow charged sphere, inside at any point intensity is 0. At any point on the surface, intensity is 1 by 4 pi epsilon naught charge on the sphere by radius of sphere square. Intensity at any point outside, which is at a distance small r, that point is at small r distance from center of that hollow sphere. Their intensity is 1 by 4 pi epsilon naught q by small r square. So this intensity in various cases and its relation with the distance of the given point, this you revise regarding that intensity of the field. Then when it comes to Gauss law, the flux passing through the Gaussian surface, depends only on charge enclosed inside that sphere. Flux independent of charge outside. Flux passing through a Gaussian surface due to charge present outside that Gaussian surface is 0. Flux is only due to charge inside. And flux doesn't depend on size of the Gaussian surface and shape of the Gaussian surface. Suppose there is a point charge Q. I'm assuming one sphere around this of radius 5 centimeter. The flux passing through this sphere of radius 5 centimeter, suppose 5. Then around this point charge, if we assume another sphere of radius 10 centimeter, through that bigger sphere also, Flux passing through that sphere of radius 10 centimeter also 5 only. Same flux, same field lines pass through it. Flux doesn't depend on size of Gaussian surface, shape of Gaussian surface, and the position of the charge inside. Wherever this charge is present inside that, flux will be same. So these theoretical points, conceptual points, focus on them. Now let us start some problems now. See this first problem, this is based on Coulomb's law. Force between 2-point charges in vacuum at a distance r is F. So there are 2-point charges. They are separated by a distance r in vacuum, and the force exerted by them on one another is F. Means this F is 1 by 4 pi epsilon naught Q1 Q2 by R square. This is given. Now the force between them, when they are placed in a medium of dielectric constant K given. So if these two charges are placed in a medium of dielectric constant K, then the force F dash will be 1 by 4 pi epsilon naught epsilon R. What is epsilon R? Relative permittivity of that medium. Means also called as dielectric constant K. Q1, Q2 by R square. Now what is given? There is some medium of dielectric constant phi between these two charges, and he changed the distance also. Earlier distance is R, now it is R by phi, distance decreased. So 1 by 4 pi epsilon naught Q1, Q2 by this K value given as phi, and this new distance R by phi they gave. R by phi square I am writing. R square by 25. Then one phi cancel now here. Then that phi will go up. So you'll get F dash is phi times of 1 by 4 pi epsilon naught Q1, Q2 by R square. This is nothing but previous force F. So F dash value is 5F B. So like this is based on Coulomb's law. Now in this Coulomb's law, one more point I want to discuss here. When two charges are in air or vacuum, suppose in air or vacuum, two charges are separated by some r naught distance. Two charges are there. They are separated by r naught distance in air or vacuum. Then the electrostatic force exerted by them on one another will be 1 by 4 pi epsilon naught Q1 Q2 by R naught square. If this same charges are kept in a medium, if the same charges are kept in a medium of some dielectric constant K, relative permittivity K, then the force between them decreases by K times. When I maintain same distance between them, force decreases by K times. But I want same force between them. Even when they are in a medium, same force like before I want. Then I should decrease the distance between them because force decreases now. I have to increase that force back to this value. So I have to decrease distance. Suppose these two are separated by another distance in medium Rm I am taking. Distance in the medium. Now the force is 1 by 4 pi epsilon naught Q1 Q2 by K Rm square. What I want is, I have reduced the distance between them so that the force in both cases is same. So this force exerted by them when they are in air, this force exerted by them when they are in medium, both are equal. If I equate these two, 1 by 4 pi epsilon naught Q1 Q2, they are cancelled. You will get R naught square is K into Rm square. Means R naught is root K into Rm. That means Rm must be equal to R naught by root K. You must decrease the distance by root K times. If you want the same force in that case also, you must decrease the distance by root K times, where K is the dielectric constant of that medium. This is another important point in this Coulomb's law problems. In this Coulomb's law problems, one more important thing is, suppose if the total distance between two charges is air only, occupied by air only, then the force exerted by them is this 1 by 4 pi epsilon naught Q1 Q2 by R square. If the total distance is occupied by one single medium of dielectric constant some K, then the force exerted by them is 1 by 4 pi epsilon naught Q1 Q2 by K into R square. But if multiple media are there, suppose between these two point charges, some distance R1, one medium of dielectric constant K1 is present, remaining distance R2, another dielectric constant K2 is present. Multiple media are there. Then how to find force between them? If one single medium is there, you can apply this Coulomb's law directly and find. Na? If multiple media are there, the procedure is, you consider like this. In place of this first medium of dielectric constant K1 occupying a distance R1, if air is there, it should occupy a distance of root K times of that medium distance. So what I am doing, between Q1 and Q2, there is air here. Instead of this first medium, air I am taking, air or vacuum, which is occupying a distance of root K1 times of R1. And this second medium of K2 occupying R2, instead of that also air I am taking. But how much distance? So root K2 into R2. Then this is the equivalent distance to have same force in both cases, with air between them, with a dielectric medium between them to have same force. The relation between distances is, distance in air is root K times distance in medium. So distance in air, root K into distance in medium, I wrote. So assume full air is there, but the distance between them is not R1 plus R2. It is root K R1 plus root K2 R2 is the effective distance between them you take. That means the effective distance to have that same force is root K1 into R1 plus root K2 into R2, you assume. Now write the force. This total distance is occupied by air only, air or vacuum. So 1 by 4 pi epsilon naught Q1, Q2 by this effective distance square you write. That is root K1 into R1 plus root K2 into R2 whole square. That is formula application of Coulomb's law when multiple media are present between two charges. For example, let us see one problem. Suppose they gave force between two charges separated by a distance r in air is f if a dielectric slab of k equal to 4 and some thickness, let us take thickness r by 3 is kept between them, then the force is dash. Suppose this given force between two charges separated by a distance r in air is f. If a dielectric slab of k equal to 4 and thickness r by 3 is kept between them, then the force between them is dash. So here, between these two charges, when air is there, force is 1 by 4 pi epsilon naught q1 q2 by r square. But between these two charges, which are separated by r distance, if you put a dielectric slab of thickness r by 3, this remaining distance here, air only there, na? Means how much distance air occupying here, air, how much distance it is occupying? Total distance r minus thickness of this dielectric slab r by 3, if you subtract, 2r by 3 distance air only occupying. R by 3 distance, this slab is there. Now find the new force applying this multiple media formula 1 by 4 pi epsilon naught q1 q2 by root k1. Air medium first I am taking. Dielectric constant of air is 1 root 1. R1 distance occupied by air, that is 2r by 3 plus root k2 root 4, that slab dielectric constant, and R2 distance occupied by this slab r by 3 it is. This is effective distance, its whole square. Then root 4 is 2. This is 2r by 3 plus 2r by 3. 2r by 3 plus 2r by 3 means 4r by 3. So you are getting like this. F equal to, F dash equal to 1 by 4 pi epsilon naught q1 q2 by 4r by 3 whole square. This 9 will go up, 16 is there. So you are getting 9 by 16 times of 1 by 4 pi epsilon naught q1 q2 by r square. This is previous force F when they are in air. So it is 9F by 16 is answer. So like this, these are different models, important models on Coulomb's law. Okay, let us go to next problem now. See here, three charges of magnitude 100 microcoulomb all have same magnitude 100. Equilateral triangle. So first I am drawing equilateral triangle. I am drawing A, B, C. At all three, same charges are there. Magnitude of charge same. Triangle length, side length 4 meter given. At points A and C, positive charges are there. At point B, negative charge is there is giving. So this is positive charge. This is also positive charge, but this charge at B is negative charge. Now the magnitude of the total force on the charge at C and the angle made by this force with AC is asking. So on this charge at C, what is the net force is asking? Net force magnitude and net force direction, what angle it will make from AC. This is asking. That only I told you, vector addition, this all we need to apply. So first you observe individual forces. This charge at corner A, vertex A, plus Q charge will repel this plus Q charge this side. So that repulsion force F I am taking. It will act along this line outward. As this vertex B, their negative charge is there. This negative charge will attract this plus Q, which is at C. That attraction force applied by minus Q and plus Q will act towards this. That is also F only. Same, these two forces are equal because charges magnitudes same and distance same. No? So same force these two will apply on that. And these two forces are inclined by 120 degrees. Now in vectors, you know now if two equal forces are inclined at 120 degrees, the resultant is equal to either of them. F only. F only. The resultant force root F square plus F square plus 2 F into cos 120. Cos 120 minus 1 by 2. 2 to cancel. Minus 1 by 2. 2 to cancel. This will become minus. Minus F square you'll get. Minus F square plus F square cancel. 1 F square remain. Means resultant is F only. If two equal forces are inclined by 120, the resultant is F only. And this resultant force will bisect the angle. It will act at equal angles from both the forces. So the resultant force is F and it makes an angle 60 degrees with each of these two lines. So this F is acting at 60 degrees from AC. He's asking that angle there. Angle from AC, it is 60 degrees. So either first option or second is correct because in these two, 60, 60 is there. Now magnitude of this force is equal to either of these two forces only. Na? So find it. 1 by 4 pi epsilon naught, 9 into 10 power 9 into Q1, Q2. This charge into this charge. 100 microcoulomb, na charge. 100 microcoulomb means 10 to the power of minus 4. Q1 10 power minus 4, Q2 also 10 power minus 4. 10 power minus 4 into 10 power minus 4. 10 power minus 8 I will get. By R square, 4 square, 16. Simplify that, you'll get the magnitude of this force. So this is also based on Coulomb's law, but this is superimposition principle, two forces acting, their net force, resultant force we are calculating. Okay. Now let us move to next problem. Okay, this is also based on Coulomb's law. A small uncharged conducting sphere. One sphere is there, it is uncharged. Is placed in contact with another identical sphere, both are of same radius. Having a charge, it has a charge 4 into 10 power minus 8 coulomb. They are brought in contact, uncharged sphere, charged sphere, and then separated. Okay, in this case, when you bring them in contact, conduction takes place. During that conduction process, whatever total charge is there, the total charge is redistributed among them till their potentials become equal. Charge transfer takes place till potential becomes equal. Charge transfer takes place during conduction. Potentials of these two spheres must be equal finally, not charges equal. Potentials must be equal finally. Potential of a sphere, you know, 1 by 4 pi epsilon naught q1 by radius of sphere. 1 by 4 pi epsilon naught q2 by radius of sphere. That means q1 is to q2 must be equal to r1 is to r2. Means the charge is redistributed among them in this ratio. Whichever sphere has more radius, that will gain more charge. Whichever has less radius will have less charge finally. But in this problem, they are identical spheres given. Means radius 1 is to 1. So charges also 1 is to 1. Means they will share this charge equally. That means first this uncharged sphere earlier, now will have half of this charge. 2 into 10 power minus 4 coulomb. The other also will have now 2 into 10 power minus 4 coulomb. They are separated by some distance. Force between them given here, 9 into 10 power minus 3 is asking distance. So apply that Coulomb's law again, solve it. F is 1 by 4 pi epsilon naught q1 q2 by r square. R square is equal to q1 q2, both are same. 2 into 2, 4, 10 power minus 4, 10 power minus 4, 10 power minus 8, q1 q2. 1 by 4 pi epsilon naught 9 into 10 power 9 by this f 9 into 10 power minus 3 given. From this find r. 4 is there, 2 you will get. First option. Okay, let us go to next problem. 2 point charges q and minus 3 q. Q. Immediately, if you start drawing diagram like this, quickly you can solve problem. Q and minus 3 q are placed at some distance, some r. If the electric field due to minus 3 q at the location of q is ei cap given. What is the mean? What does it mean? Electric field at the location of q due to minus 3 q. What is meant by electric field? Force experienced by unit positive charge. Means at the location of this q, suppose if there is a unit positive charge, due to this minus 3q, this unit positive charge will experience some force. That is intensity of electric field at this location due to minus 3q. That is giving as E. What force it will experience? Attraction force towards that negative charge. And this E value how much? 1 by 4 pi epsilon naught 3q into 1, 3q by r square. And this is acting along positive x-axis. That's why he is writing I cap. Now he is asking the electric field due to q at minus 3q. That means here q is there. At minus 3q, assume there is a unit positive charge. Then because of q, that unit positive charge will experience how much force? You find. What is that force? This is positive charge, this q. It will repel it. So away it will act. E dash. Away means it is acting along positive x-axis only. And this E dash value, 1 by 4 pi epsilon naught, q into 1, q by r square. I cap only, because it is repulsion acting along positive x-axis only. This you have to express in terms of E. 1 by 4 pi epsilon naught q by r square is E by 3. No? This. So E dash is E by 3 into I cap. E by 3 into I cap. Right? Going to next. A point charge. Point charge. 0.009 microcoulomb. I'm writing like this. 0.009 is 10 power minus 3. Now 9 into 10 power minus 3. Micro means 10 power minus 6 now. So this is 9 into 10 power minus 9 coulomb. First I'm changing like this. Is placed at origin. So this charge is placed at origin. Which charge it is? Positive charge. Positive. No? Any sign not given means you must take the charge as positive. This charge is kept at origin. And is asking calculate the intensity of electric field due to this charge at a point. That point coordinates are given. And if you observe here in vector form, he is giving this answer. That intensity in vector form. You have to write now in vector form. What is intensity due to point charge formula? 1 by 4 pi epsilon naught q by r square. This. Suppose there is a point here, P. At this point, distance from charge to that point is r. Then intensity formula is this. But this in vector form you have to write. Means if r bar is the position vector of this point with respect to the position of charge, this point position vector, if it is r bar, and in vector form, if you want to write it, assume the unit vector in this direction of intensity, unit vector is r cap. So E bar equal to 1 by 4 pi epsilon naught q by r square into r cap you have to write. Then this E bar equal to 1 by 4 pi epsilon naught q by r square into what is the unit vector along this position vector line? What is the unit vector? If you divide this position vector with its own magnitude, you will get unit vector along this direction. So this r cap is r bar by magnitude of r bar. Magnitude of r bar, r I am writing. Then you will get E bar equal to 1 by 4 pi epsilon naught q by r cube into that position vector r bar. Yes, finish. E bar equal to 9 into 10 to the power of 9, 1 by 4 pi epsilon naught. Q is this 9 into 10 power minus 9 Q value. R bar coordinates given, this point coordinates, that means the position vector of that point is this x coordinate root 2 into I cap plus this y coordinate of that point root 7 into j cap, z coordinate anyhow 0 given. So this point position vector, this OP bar is root 2 I cap plus root 7 j cap. That is only this r bar. So write it root 2 I cap plus root 7 j cap by r cube. R cube means the length of this position vector magnitude. What is the magnitude of this r bar? R bar magnitude under root this x coordinate square root 2 square 2 plus root 7 square 7 root 9, that means 3. So this r is 3. 3 cube you are getting 27. 27. These two cancel. 9, 3 times here. 3 into this. 3 into root 2 I cap plus root 7 j cap. Second option, 3 into root 2 I cap plus 3 into root 7 j cap. Very important problem. Expressing intensity in vector form. Okay, I'm moving into next. Field lines. Choose the correct option for this electric field lines diagram. Two charges are there. He is asking which is positive, which is negative, which charge is more. What you have to apply? Where the field is strong, there the field lines density more. And if the charge is positive, field lines come out of that. If the charge is negative, field lines go into that, towards that. If you observe, this is small q charge, this is capital Q. Arrows are shown towards capital Q. They are going towards capital Q. Means a test charge, a positive unit positive charge moves towards capital Q. Means capital Q is negative. And that small q charge, field lines coming out of the small q. Small q is positive. And field lines density is more, they are very near closure and density more near small q than when compared with near capital Q. Means small q is magnitude of small q is greater than capital Q. That means capital Q is less than small q. That is answer. Q, capital Q, small q positive, capital Q negative, and capital Q less than small q. Yes. Third option, I think. These are important models, these are. This is Gauss law flux. A linear charge having linear charge density lambda means a wire, charged wire of charge density lambda penetrates a cube diagonally. So through that cube, that wire, long charged wire is arranged along the diagonal of that cube. Positively charged it is. And through a sphere also. This type wire is arranged through a sphere along diameter. Radius of sphere A, cube side length A. What is asking is, what will be the ratio of flux coming out of the cube and sphere? First cube I am taking. What is Gauss law? Flux passing through a closed surface is the net charge present inside, enclosed inside it by epsilon naught. If the medium is air or vacuum, epsilon naught. So, how much charge of this wire is enclosed inside this cube? That I have to substitute here. For that, what to do? This lambda, linear charge density. Linear charge density is lambda. What is it? Total charge present on it by length. Then what is the charge on this wire? On a portion of this wire, what is the charge means? Lambda into length of that portion by epsilon naught. So what is this portion length. Whatever portion of this wire is embedded inside cube, that portion length. That length is nothing but body diagonal of this cube. What is the body diagonal length for any cube? Root 3 times the side length. No? So this will be lambda into root 3a by epsilon naught. And then I am taking the other closed surface sphere. What is flux through this? Lambda into the length of the portion of wire which is present inside this. How much length is inside this? That length. That length is nothing but diameter. Radius A given, diameter 2A by epsilon naught. Ratio of these two is asking root 3 by 2. Third option. Now in this cube, another type of question they can ask here. A long charged wire of linear charge density lambda is arranged through a cube. What is the ratio of minimum and maximum flux that can pass through the cube? They can ask. Flux will be maximum when maximum length of the wire is inside of the cube. And flux will be minimum when minimum length of the cube wire is inside of the cube. Maximum length of the wire means if you have a cube like this, if I want to arrange a long wire passing through the center of this cube, it should pass through center, okay? I can arrange it like this. I can arrange it along the body diagonal. In different ways I can arrange, but the wire should pass through center. In these different ways, maximum length of the wire will be present inside cube if you arrange it along diagonal. How much length? If the side length is A, root 3A is of the wire is inside. In that case, flux will be root 3A lambda by epsilon naught. That is maximum flux. And if you arrange the wire through center parallel to any side length, then minimum length of the wire will be inside the cube. That is A only, minimum length. Then the charge present inside is lambda into that length only. Means minimum flux is lambda A by epsilon naught. They can ask this also. What is the ratio of maximum and minimum flux that can pass through the cube when you arrange a long charged wire passing through its center? They can ask. That answer is root 3:1. Going to next, the figure shows the path of three charged particles in a uniform electric field. Which has highest charge to mass ratio, Q by M ratio. So here there are two charged plates. This plate is positively charged. This plate is negatively charged. And there is a field here, field of these plates. What is the direction of that field? So let us take this horizontal line as x-axis and this direction as y-axis. Let us take. Here field is along which axis? Field means if you put just test it like this. If you put a unit positive charge, because of these charged plates, this unit positive charge will experience force in which direction you observe. That is field direction. it will experience force towards negative plate now. So here electric field is along y-axis, along negative y-axis. Electric field of these plates is along negative y-axis. Now here three charged particles entering into this field like this. Path shown there like this. Means these charged particles are entering perpendicular to field direction they are entering. Means this charged particle has initial velocity along x-axis. There is no initial velocity along y-axis. It has initial velocity only along x-axis. Now, this charged particle, if it is positively charged particle, it will deflect like this. If it is negatively charged particle, it will deflect towards that positive plate. Why? Due to electrical field, they are deflecting. If it is positively charged, electrical force EQ will act in the same direction of field, this side. If it is negatively charged particle, if it is negatively charged particle, on that negatively charged particle, electrical force EQ will act opposite to field direction, like this. Due to this force, it has to deviate. So here what you have to do is, you find in a particular time t, what is the displacement perpendicular to field. Displacement perpendicular to field means displacement along x-axis. Take it as some x, the displacement, ut plus half at square, you apply. X equal to, along x-axis only, no, it has initial velocity u, ut will get. Along x-axis, there is no force here. Electrical force is acting along field direction, this EQ. There is no force along x-axis. As there is no force, there is no acceleration along x-axis. There is no acceleration perpendicular to field. In electric field, perpendicular to field, acceleration will be 0. So x equal to displacement in a given time, displacement along x-axis is ut. Next, you find the displacement parallel to field, electric field direction. Displacement parallel to field when you find, that is suppose y you take, ut plus half at square. Along field direction, there is no initial velocity. At the time of entry, it has velocity along only x-axis, not along y-axis. Initial velocity is 0, ut is 0. Half into along field direction means parallel to field direction. Along y-axis, due to this force, electrical force EQ, acceleration will be there. That acceleration is force EQ by mass into t square. This is displacement along field. This is displacement perpendicular to field. Motion of charge in electric field. From this first equation, I can write T is x by u. That if I substitute here, I will get y equal to half into EQ by m into, in place of t, x by u, x square by u square. Now you see here, the charged particles are displacing along x-axis as well as along y-axis. Along y-axis, along field direction, the displacement y is proportional to q by m. Specific charge. Which particle is getting more displacement along y-axis? This third particle, more deflection is there. Why more for third particle? Mean third particle q by m, specific charge is more here. So is asking for which particle that specific charge, ratio of charge to mass is more. Third particle. Okay, students. So all the best to practice all these types of theoretical concepts. NCRT book revision you do on NCRT lines, diagrams in NCRT, graphs in NCRT, focus on them, revision is important. This chapter is conceptual. Learn those concepts properly. Okay, right. Thank you.